whatever. Okay, so quick recap from last time, though there's not much to recap. If you cannot hear me, just let me know. We did look at locally analytic, we just introduced locally analytic representations. By introduced, I mean we briefly talked about why this is important and why we should look at them. So this was introduced by Schneider and Teitelbaum, I think actually in 1999. And then a bunch of other papers. But anyway, so we did introduce locally analytic representations. Basically, the point is to find a good category of periodic representations, which is better than continuous representations in the sense that it does not have the pathologies that a general continuous periodic representation has, but also broader than smooth and finite dimensional algebraic representations. And locally analytic representations turn out to be the right category for a lot of things. Of course, we'll see eventually if we get there, hopefully we do, that instead of dealing with all locally analytic representations, sometimes it's beneficial to deal with just these so-called admissible locally analytic representations. And a lot of the representations occurring in nature is admissible. So we don't lose much if we assume that we are dealing with admissible locally analytic representations. And we'll talk about these categories or much more in the coming weeks. But today my goal is to do something that's impossible given how less I know of this subject. But so, like how people write, how we could have invented spectral sequence. To write that, you really need to know what spectral sequence is. And then there are people who write like review articles on stuff. So my goal is to review locally analytic representations without knowing most of it, which is a bizarre goal. And it's probably mostly self-serving, but hopefully it will be useful for some of you or not. We will see. But the goal here is today's goal. Brief overview of places where locally analytic representations show up. And I had a novel idea while preparing this talk. Maybe not novel, maybe it's a terrible idea, and probably other people have done this too. But what I'm going to do is more or less talk about abstracts of fundamental papers in this field. My knowledge of most of those papers are restricted strictly to the abstract. So if you ask me to clarify or ask me like what they're actually doing, I'll be like, well, can you please read it and tell me sometimes? But I think there is some joy to be gleaned out of just reading the abstracts and kind of seeing like what the things are. So that's my attempt. If it is terrible, let me know. But now that you're all here, I might as well say something. Okay, so first of all, let me talk about, so let me briefly introduce these things that we'll require later. So first, let me talk about locally analytic functions. Okay. As the name suggests, locally analytic functions are functions which are locally expressible as convergent power series. Functions for which every point, every point in the domain has an open neighborhood where, if the handwriting is not visible, please let me know, where it is expressible as a convergent power series. Of course, you'll realize that this is a colloquial definition because convergent power series, convergent where? what are my coefficients, and so on. But locally, these are functions which are expressible as convergent power series. And right now, I'm not going to explain more on this, but like let me just talk about examples. So the most trivial example that you can look at is locally constant functions, right? If you have locally constant function around every point, there is a neighborhood where the function is constant. Of course, you can look at polynomial functions. And so on. Okay, so before I move on, functions on where? Well, so the domain usually is a p-adic manifold. Later we'll talk about what it exactly means, but domain usually is ZP OF for some finite extension f of QP, GLN QP, GLN ZP, etc. My point is to say that the functions you're looking at will be functions on these kind of spaces. So they are p-adic manifolds in some sense, and we'll talk about that precisely maybe in the next talk or the talk after. But the domain are usually this, so they have a p-adic topology, and you can make sense of convergence. Okay? If you have any questions, please do stop me at any point. Of course, you can have globally convergent functions, globally convergent power series. So for example, if you have a function ZP to, let's say, some finite extension E of QP, finite field extension, obviously, F, so what does it mean to be globally convergent? It just means that there exists a power series which is equal to F in this case, and it converges in all of ZP. And of course, if it converges in all of ZP, then locally it is a convergent power series, so it's a local analytic function. These play an important role. Particular cases, these are example of rigid analytic functions. Of course, I should say more about them, but so there is more to that, but these are rigid analytic functions, and they will play an important role in the theory of locally analytic representations as well. And I think we'll see that as soon as next talk, where we'll talking about locally analytic functions of ZP. So these are usual examples of locally analytic functions. And then let me talk a little bit about locally analytic representations, at least formally. Locally analytic representations. So what is a representation? I mean, of course, this is a naive reminder, and all of you know this, but a representation is a vector space with the action of a group, right? So we have a V and we have an action of a group G, okay? So a representation of G given by V is called locally analytic, if for every V, you have the map, the orbit map is a locally analytic V-valued function for every V. Okay. Does this definition make sense? Yes. So for example, what do you mean by V-valued locally analytic function? Well, so remember that, let's say you have a manifold. Let's say you have a p-adic manifold, whatever that is. That means that around every point there is a neighborhood from which you can say go to ZP to the D, or like, so you have a map or a chart around every point which goes to ZP to the D, and you have a function F that's going to V, right? You call this locally analytic V-valued function if this map is actually locally analytic V-valued function. And what does that mean? Well, so you have this map, I want to call this F, and F is a map from ZPD to V, which is a vector space over E. So I want that F should be equal to some power series, locally expressible. Of course, this is local with C alpha X alpha, where C alpha is in V and X bar alpha is the coordinate chart. Is this making sense, or am I just being completely meaningless? Does this make sense, more or less?
So V is supposed to have a norm, I guess.
Yeah, V is, that's a good point. I mean, usually V is a locally convex vector space. So it has a notion of convergence. Sometimes it can be given by semi-norms. These are probably not normed spaces. As such, we'll have like topology given by a family of semi-norms, but it has a notion of convergence. So these C alphas are in V, and so this function converges in V. Okay. So that's locally analytic representation, where all of these maps that you get. So I mean, G is acting on V. So if you fix V and make it act on the left by G, then you get a map from G to V. And you want this map, just like G, treating G as a locally analytic manifold, you want this map to be locally analytic. Okay. So that's basically locally analytic representations definition. Of course, when we do Schneider Teitelbaum, we'll refine this. So what condition does V need? That's important. And then there's slight wonkiness to this definition, where defining V valued is not exactly like this under certain cases. So if, for example, G is compact, you can pretty much say this, but usually it requires some extra conditions. So like then you look at subspaces of V, which has a norm like Banach spaces, and then you look at inductive limits and so on. So let me indicate precise definition in Schneider Teitelbaum JAMS paper. I don't know. I think this is the periodic distribution algebra paper. And maybe talk 3 or 4. I think that's probably a good target. Anyway, so what are good examples of locally analytic representations? Let's look at examples. We are going to look at some of these examples pretty carefully later, and I'll try to explain why they are important. But for example, the most trivial, not trivial, the most natural example that you can think of is the locally analytic functions with E. So remember, for me, my convention is always that these are finite extensions of QP, and F is the field that goes inside. So we are looking at F valued points of an algebraic group, and E is the coefficient field. So CLA-GE is the locally analytic functions on G, locally analytic functions on G. If G is compact, this is a locally analytic representation. So here I have a confusion for a long time, and I should figure it out. I'm too lazy. But the point is that, okay, so why do we assume compactness? Because remember, we are talking about V being a representation, and then because it's topological, so we need topological restraints on V. And if G is not compact, then the space of locally analytic functions in itself is not very good. It does not satisfy the conditions you need for a representation to be locally analytic. But if you do take a non-compact space and a non-compact group and look at this space, you can totally do that. I wondered like whether, and of course I have done some work on this. So like you can break it down into the local analytic functions coming from the compact, maximal compact, and then cosets of that. But what kind of space that is, I think that needs some thought. But anyway, if G is compact, then looking at the space of locally analytic functions of G gives you a locally analytic representation. How does that work? If you have a function f inside this space, and like don't hate me if I get this wrong, but how does this work? the action of G is given by how you would expect it to be given by, something like this, or, okay, that makes sense. Okay, so here let me put an asterisk. Talk 3, I think, should be entirely on CLA CPE. So you'll see that even if you're looking at the periodic integers, just the ZP, the locally analytic functions on ZP are quite interesting. And through this machinery of Mahallar series, there will be something called a Fourier transform. And we'll see that there is an isomorphism, a non-trivial isomorphism between the dual of this space CLA-ZP and space of overconvergent functions or space of globally analytic functions on some rigid analytic space. And that's an important fact that sort of motivates the further definitions that we'll see in Schneider-Teitelbaum. But also another thing that it motivates is periodic Fourier theory. And I think like when you're talking about that, giving some motivation or indication of like how periodic Fourier theory works should be good. Okay, where else do we see locally analytic functions? Well, continuous characters of ZP. So this is chi from ZP to E star, which is both of them have periodic topology. You can define continuity, are all locally analytic. Quite surprisingly, if you look at continuous characters of ZP, they turn out to be locally analytic. But of course, if you change this, but if replacing ZP by OF, where F is as above finite extension of QP, proper finite extension of QP, then this does not quite hold. For F analytic representations. Okay. So when I was defining locally analytic, I did not mention this, but of course, if you have extensions of QP, you can treat function as either QP analytic or F analytic, right? An analog of that you see in real numbers. If you have a function from complex numbers to somewhere, you can treat it as a smooth function from R2 for getting the complex structure. But if you include the complex structure, the analyticity poses a stronger condition, right? A smooth complex, complex analysis brings extra tools. So if you demand that it be complex analytic, it's a stronger demand than it being just R2 analytic. Similar things happen here. If you have a finite extension of QP, if you demand it to be F analytic, you will see that not all continuous characters are F analytic. You need some condition on the derivative. In fact, you need the derivative to be F linear, exactly. Does that make sense? Okay. I'll assume that silence is just acknowledgement. Otherwise, please do stop me. Where else do we see locally analytic representations? Let's indicate some important examples. So locally analytic induction. This is also extremely important, and we'll come back to this, I think, in fourth lecture. If you are following Schneider-Teitelbaum, we'll look at specific examples of this. What's the setup? So let's say you have G, and you have, let's say, P, which is parabolic, whatever this is. And you have the maximal torus, diagonal matrices set. If you're looking at GL2 or GLN, for example. Okay. Then what you can do is look at a representation, look at a character, say, or I mean, why a character? Start with start with a representation V of t. By representation, I mean locally analytic, and treat it as a P representation by making the rest act trivially. If any of this is true to verbose, I'll just give a concrete example soon. But if you have a representation of T, you can think of it as a representation of P by forgetting the action on the off diagonal part, so to speak. Now you look at this space, the locally analytic induction. How is this defined? This is defined very much as any induced representation. These are functions from G to V, okay? Such that if you take P, so how do I want this to go? I think P dot f of G should be I want to call this V. How do I want to call this? Okay, so well, so if you take P in P in P, then for any V, P acts on, remember that V is a representation of P, so P acts on V. So you want this to be f of P times G to be P dot f of G. Okay, here is probably an inverse somewhere. Let me act P inverse, something like this. Does this make sense? So if you have P acting inside G, you can pull it out, and then this is the action given by the representation V. Okay. Make sense? Yes? No? Okay. So if you are looking at an example, let's say G is GL2, QP, maybe. T is the diagonal matrices. So a representation of that, like let's look at a character chi, and then let's take P is equal to B, which is upper triangular matrices. And then how does chi extend to this? Well, chi extend trivially. By that I mean chi of star star is same as just this. Okay, and then you can look at in GB chi. This is called the locally analytic principal series, and these are quite interesting objects in their own right. This plays an important role in periodic local Lagrange. They show up everywhere in Emerton's completed cohomology and so on. Okay. Okay, where else do we see locally analytic representations? I'll mention a few more, maybe. But how are we doing on time? Well, that's fine. So there is a rich source of locally analytic representations coming from Drinfield upper half space. Drinfield upper half space and periodic uniformization. This you can find maybe in the work of Schrein. No, not Schrein. Dospines Culebra and Colmes, etc. So you have the periodic upper half space, which is a rigid analytic space, and you can have very much in the vein of complex uniformization. You can have uniformizations of the periodic upper half space. This is a fundamental work done by Drenfeld and others. So you have this periodic upper half space, let's call that sigma 0. You have a tower of rigid analytic spaces for every n. It goes infinity. So there's an infinite cover of rigid analytic spaces, and you can look at, say, H1 of with, I don't know, something like this. H, don't quote me on something like this. You can look at these cohomology spaces, and they will have an action of G, where G is, let's say, GL to QP. Okay, so this produces a series of or sequence of representations, locally analytic representations, which are quite important. And if you remember that this showed up, the first one showed up in Morita's work. So earliest examples of locally analytic representations kind of comes from this. Okay, and this is very interesting field of study. Like if you want to read periodic uniformizations, which I never managed to read myself, Boutillot-Carriol is the paper to go to, which tells you how to construct these spaces. And then looking at these representations, you can ask, for example, we mentioned before, this category of admissible representations. Are these admissible? And one of the fundamental works I think these people do is that they show that these are indeed admissible. And I think there are a lot of interesting work to be done in this whole area as well. Okay, and then I think I want to mention this because I have vested interest in this, and I think so does Akash. Orlik Strauk and Functor produces a lot of interesting locally analytic representations. I think it will be good if we can manage to get to this paper itself. I don't know how feasible that is, but what happens here is that you have this category O. This is the so-called BGG category introduced by Bernstein, Gelfand, and Gelfand. I don't know why saying these names give me any pleasure. I don't think this should mean anything to anyone. So we have this category O, which is the so-called BGG category. This has been studied by Lie group and Lie algebra people for a long time, Lie groups and Lie algebra people. And I mean, significance of this, I think both like Jamil and Akash knows much more than me. I don't really understand this very well, but we have had this category in the background for long enough. And then Orlik Straub, what they did, they introduced a functor from this category to locally analytic admissible. I mean, of course, I can throw the admissible in, but this sits inside locally analytic representation. But so there is a functor from this category O to the locally analytic representations, and the image of this functor has a lot of interesting locally analytic representation. In fact, if time permits, like I'm going to go over an abstract of a paper that's really recent by Strauk and Agarwal, where they show that the image of this functor consists of really interesting representation that appears in periodic local Lagrange program. Also, I mean, I would be remiss if I don't mention this. Another source of locally analytic function representations is Lubin-Tate tower. So, I mean, whoever has taken class field theory knows that we can do class field theory completely via Lubin-Tate tower, which is a series of extensions you construct or Lubin-Tate constructed, and there is a geometric aspect to that, and that geometric aspect has been really interesting for periodic people for a long time. For example, you can see a lot of Scholz's perfectoid spaces works done in the Lubin-Tate setting, like Cariani, Scholz, and all these people. I never understood any of those works. I know too little math to talk about them, but Lubin-Tate towers are interesting, and there are representations coming from them that parallels uh, Drinfeld tower somewhat. And you can ask interesting questions. So for example, you can ask, okay, there is another tower. It is giving you a sequence of representations. Are those admissible? And I think it's not known. Don't quote me on this, but I have been told that it's still not known. It's not known if these representations are admissible. And I think it will be an extremely interesting work if anyone can do this. Um, Okay, so those are, I think, main examples of local analytic representation. And of course, I should add from periodic local Lagrange. Okay, and we'll talk about this later. Now, let me jump directly into what I intended to do. And I think I took too long in this introduction. I'm going to talk about some abstracts, really. So first, okay, so this, let me call tools of local analytic representation. And the first paper that we are going to talk about is this fundamental paper. This is called local analytic distribution. This is the paper that I think we are going to read after this talk. Well, right after this talk, we'll all go and read this paper. Local analytic distributions and periodic representation theory. With application to GL2. This is Schneider-Teitelbaum, the OG paper. So what do they do? Or what do they say in the abstract, rather? Because what do they do is, we are going to understand that, but they say that we cannot, this is repeat from last time, we cannot deal with continuous representations completely because A, no unitary representation, B, even local analytic functions are not integrable with respect to Haar measure, which, if you remember, well, I don't know. I don't remember because I don't know. But I have been told that for smooth functions being integrable with respect to hard measures play a very important role in the theory of smooth representations. That's the harmonic analysis part that kicks in and about which I don't know anything, but it exists. And we don't have an analog of that for all continuous representations. And so then you have technical difficulties like no algebraization. For smooth representations, so I mean, the point I'm trying to drive home is that we kind of want to mimic smooth representations. We know smooth representations are good. We have had years and decades of experience dealing with smooth representations, but we don't know how to do that for continuous representations. So we're trying to find what representations can you have so that it extends smooth representations repertoire. And algebraization, which is looking at modules over Hecke algebra, is one of the important tricks of smooth representations. We don't have that for continuous representations. Okay. So then they introduce. So what they do in this paper, introduce an abelian category of continuous abelian subcategory of continuous periodic representations. And in fact, they call this category, so I'm going to be skeptical about this. Admissible locally analytic representation. Okay, so they introduce admissible locally analytic representation in this paper, but this definition changes. The current definition we use is not this definition. I think this is now called strongly admissible or something like that, but this definition has changed. Uh, what they managed to do, so what's the thrust of this paper? Questions, topological questions turned into algebraic questions. Let me give a concrete example because this is too vague. So to prove irreducibility of locally analytic representations, this is always an interesting act, right? You want to show that some representation is irreducible. If you can find irreducible representations, they're always good because they're building blocks of other representations. And showing that some locally analytic representation is irreducible is a hard task in general. And they find a technique. So to show certain representations are irreducible, they show that this is equivalent to showing simple module over distribution algebra. Okay. So this is what they do in this paper. They show that you can translate a lot of these interesting representation theoretic functional analytic questions to questions about algebra. You have this distribution algebra. To show something is irreducible, you just show the corresponding module you get is distribution algebra. Okay. Does that make sense? Sort of? Yes.
Yes.
Okay. So then what do they do in the other paper? I am so disorganized. Okay, yeah. They have the other paper, and maybe I'm just flipping these and the deep of Schneider Teitelbaum. This is the one in Inventiones. What do? They do something similar. And they develop this theory of distribution algebra. They develop the theory of distribution algebra. So remember that we did talk about distribution algebra briefly. If you have a compact group G, then you look at the locally analytic functions on G, and then the locally analytic distribution algebra, which I'm going to call DG from now on, is the strong dual of this. Strong dual of locally analytic functions on G. Okay, so this is a distribution algebra. Where is the algebra? Multiplication comes from convolution. So don't worry about this so much right now. We'll see in next talk how this works explicitly for ZP, and I think that will give a better sense. But we have this distribution algebra, and it shows that, so in this other paper, I'm calling it the other paper. I'm sure someone can tell me what this paper is actually named, but what they do is use distribution algebra to define admissible representations. This is the first time they fixed their definition of admissible representations. In the first paper, they introduced admissible representations. The condition, even though it was still given by distribution algebra, was too restrictive. So they use this distribution algebra to define admissible representations. What do we mean by that? First of all, note DG is not commutative not Noetherian. So everything that you love about commutative algebra is not there for DG. But because you can see actually in this paper, like where this motivation comes from, but DG is what is so-called Frechet-Stein algebra. In fact, when we talk about this, I should remember that there is a very beautiful motivation of this definition in this Snyder Teitelbaum paper, and this means that this DG has some algebraic structure, and you can do a lot of algebra, interesting algebra over this ring. So they introduce co-admissible, I think there's no hyphen, co-admissible DG modules. What does that mean? Well, so okay, let me take a step back. The main thrust is the duality theory. You have a locally analytic representation V. This has an action by G. You take the strong dual of it. When I say strong dual, I mean in the sense of functional analysis. Like if you have read functional analysis, which I did at some point, there is the strong and weak dual. And because this is a p-adic representation, it comes equipped with a locally convex topology. And that has a strong dual. And then this strong dual is a module over DG. This is the surprising part of Schneider and Stuhler, Teitelbaum, that they have the duality, and any dual of the strong dual of any locally analytic representation turns out to be a module over DG. Now, co-admissible DG modules are a certain class of DG modules. So you have this category of co-admissible DG modules, co-admissible inside DG modules. And you basically define this to be an equivalence almost tautologically. I think there is something there. But so if a DG module is co-admissible, if you take a representation, if it is dual is co-admissible, you call them admissible representations, admissible G representations. Does this make sense? Was that meaningful at all?
Can you repeat this again?
Yeah. So if you have a representation V, right, you want to know when I want to call this an admissible locally analytic representation, you take the strong dual of it, right? If this strong dual is in this category, in this subcategory, if the strong dual is co-admissible DG module, then by definition, V is admissible locally analytic representation. So you're using the dual to define admissibility. Does it make
we define co-admissible first, then
yeah, we define co-admissible first. So co-admissible, let me add some extra remark. Co-admissible is some finiteness condition. So co-admissibility is in particular that something is finitely generated over something.
Okay.
So you first define co-admissible, then you say that a representation is admissible if its dual is co-admissible. And in this paper, the D part is showing that there's a categorical equivalence, which is not entirely obvious, okay? Because in the definition, we are saying that if you take a representation, take its dual, if it is co-admissible, then we call that representation admissible. But that does not mean all co-admissible representations are coming from dual or co-admissible modules are coming from dual of representations, and they show that it's indeed the case. There's a categorical equivalence between admissible G representations and co-admissible DG modules.
Okay.
So this is the first thrust of Schneider's Teitelbaum's second paper. Okay, what time is it? 3:51, maybe I'll have 10 minutes. So some of the tools continued. I want to mention this other thing, Strauch. Okay, I should not start with Strauch just because he's my advisor. Patel, Schmidt, stroke. This is called locally analytic representations, and sheaves on Bruhat-Tits building. And this is named very suggestively because there is this original. So remember that, as I said, kind of the motivation for locally analytic representation comes from trying to mimic what we have in smooth representations. So this is related to my research work. So Schneider and Stuhler did this thing with smooth representations, where they associated to a smooth representation a sheaf on this so-called Bruhat-Tits building. If you don't know what that is, that's totally fine. I don't know it very well either. Well, I mean, yeah, I don't know it very well either. But they did this thing where they had a smooth representation, and to that representation, they associated a sheaf on the Bruhat-Tits building of G. So remember that I'm just talking about representations of G, and then Bruhat-Tits building is a combinatorial geometric structure associated to G. And from a representation, they constructed a sheaf. And from this sheaf, they did a lot of cohomology computations, for example. So the question was, can you do similar things for locally analytic representations? And partially, the answer is yes. Now, this is not quite the Schneider and Stuhler cut, because there is a lot of work to be done to generalize it. But what Patel, Schmid, and Strock shows that from a locally analytic representation, you can go to this thing called, you can associate a sheaf on the Bruhat-Tits tree or building. And then I think the main part of this paper comes to, you can go to an equivariant D module on some flag variety. So what this essentially does is constructs a functor from locally analytic representations to these things called equivariant D modules. And a picture to take into mind after Schneider and Teitelbaum and this paper is that you have admissible, okay, so here I should add admissible. So you have a bunch of categorical equivalences. You have admissible locally analytic representation. This is equivalent to co-admissible DG module. This is also equivalent to G equivariant vector D modules over flag varieties with extra condition. There is some condition on this equivalent D module, I believe. But what this allowed is to go from here to here via Schneider and Stuhler, Teitelbaum, and then go from here to here using Patel, Schmidt, and Strock. And then you can like look at certain problems. If you cannot do it here, then you can go here and see if you can solve it here. If you cannot do it here, you can go here and then go back and forth. So there is going back and forth. You get a whole set of tools, new tools for each of these categories. And that helps you to solve some problems about locally analytic representations. Okay. Okay. I clearly overestimated how much I can talk, so there's not a whole lot of time left, but maybe I should say something about locally analytic, so applications.
Before we end, can we talk, can you explain that part about why things change when instead of ZPU, we take OF for some finite extension of QP?
Yeah, I'll try to do that. Maybe. Okay. Yeah, I'll do that. Definitely. I'll try to do that. But so here is the thing. So
Maybe
where
we
do we
can
see
do that
applications?
next time. It's up to you.
Yeah, I mean, like, let's try to figure that out. I mean, I don't think it's pretty deep. Maybe you can see it. Let's see. But let me just talk about few applications first. So periodic local Lagrange. I keep saying this word as if this is the Holy Grail, and probably this is the Holy Grail. Uh, Here you want to look at Broyle and Berger towards a periodic local Lagrange correspondence. This is, I think, actually a fantastic survey article, and not quite survey. They propose what this local Lagrange should be towards, no, yeah, towards a periodic local Lagrange correspondence. And here they show that, so first of all, they make an important point, which I realized just today. They said, well, why are you not saying that the correspondence is between Galois representations with certain conditions and locally analytic representations? So they find locally analytic representation to be too restrictive. So the correspondence goes between Galois representations and certain continuous representations with unitary representations. So they have Galois representations here. This is very, very vague. And then continuous periodic representations on Banach spaces. And they propose what this correspondence should be, but where does locally analytic come into this picture? So let's say you have V. You have a V of G, let's say G is GLN QP. Then you define this VLA, the locally analytic functions are vectors of V, which is V inside V, such that OV, the orbit map, is still a locally analytic function on V. So this is all such V's inside V, such that the orbit map, which, if you remember, is the map taking G to G dot V, is locally analytic. So this is a subset of V, and this is the locally analytic representation that becomes important. So important result by Schneider, Teitelbaum. VLA is not equal to 0 if V is not 0. And in fact, I think it is dense. I don't know if you need extra conditions. It is dense inside V. So studying these representations V can oftentimes reduce to studying these locally analytic representations, and that has indeed been the case for a lot of this work.
So, are these like are elements of VLA called these locally analytic vectors?
Yes, yes.
Okay, okay.
Yeah. So in fact, like, where has this been important? Emerton, this is also really cool. Emerton has 3 papers, I think, that I want to not talk about. I know fuck all about any of these. Locally analytic Jacquet modules, 1 and 2. And then the other paper, this is something to do with completed cohomology. And automorphic interpolation of automorphic forms. Interpolation, I think it is called interpolation of eigenvalues of automorphic forms. Eigenvalues of automorphic forms. Actually, I strongly encourage any of you who wants to read this, like, want to understand this field, to go and read these abstracts. They have been really helpful. I was given this advice at some point and never took it. Now I'm really enjoying it. So what does he do in here? So he uses these locally analytic representations to solve a problem that's quite prominent in number theory, which is to interpolate eigenvalues using some technique. And so here, the key objects that you probably should be aware of is completed cohomology. This is a structure where periodic local Lagrange correspondence is realized. And then, of course, what is this Jacquet functor or Jacquet module? Jacquet functor. So this is good. This is something that we have talked about before, but it's the other way around. So what they do is, let's say you have the setup P is a parabolic inside G, and you have a representation V of G. So this Jack A functor, what this does is takes, I believe it's still admissible, maybe with extra, I think strongly admissible, in fact, admissible, let me put star star, admissible locally analytic functions of G, and it sends it to locally analytic functions, not functions, sorry, representations. Locally analytic, again admissible with star star, locally analytic representation of P, which is quite remarkable, JP. So they have a functor that takes a representation of G to representation of P, so simpler group. In fact, okay, so what is the other, how do you go to other, how do you go other way around? If I have a representation of P, like what's the recipe for going back? There's like basically only one thing I think we have done, right? Like what should we do to go back from a representation of P to a representation of G? Basically just look at the parabolic induction, right? And uh, and in some weak sense, these are adjoint. And this is really remarkable. So we have similar result for smooth representation. And we see that in the locally analytic case, something similar happens. And this is a really remarkable result that has many applications. Many applications. In fact, you can look at Emerton's original paper, and if you do, and then tell me, I'll be really happy. But uh, so some of the ones that you want to look at, maybe Lupan, locally analytic vectors in completed cohomology. This is, I think, a delightful result. I don't know, I don't understand the paper, of course, but it basically shows that if you have the completed cohomology and you took the locally analytic vector as prescribed above, it has a nice splitting into two direct sum of overconvergent modular forms, something that you see a lot. And then there are other things. Maybe I don't want to talk about them because I've been talking a lot. Um, but some of the other papers that you want to read, probably, or you want to like read the abstract of, probably, is there's paper by Schreien's papers. So for concrete one, look at locally analytic representation of GL3QP, something like that. And then there is also these papers by Jishnure and Klosel that I'm interested in, which is kind of tangential. They look at globally analytic representations, principal series, and Lagrange base change. Also, like there, I think there should be some work to be done in this locally analytic cohomology. Locally analytic cohomology by Kolahasi. Maybe I'll actually be not lazy and write up like some commentary on all of these. And then, of course, this is important for Akash and me, is this paper, Agarwal-Strauk, which extends and conceptualizes Ehrlich-Strauk. So they have a new preprint on arXiv, which is basically looking at their Ehrlich-Strauk construction and looking at the image of those functors, also looking at the functor closely and showing like some of these interesting properties of the functor more conceptually. Like there's this thing called PQ formula, but also they show that certain interesting representations. For example, this one shows up as an image of their functor, and they show that similarly an example constructed by Breuer for periodic local Lagrange show up as the image of the Ehrlich-Straub functor. So there are a lot of interesting works, and I missed some. I did write up notes on other articles, but they're quite interesting, I think, to read the abstracts at least. And hopefully this is helpful, I guess. Okay, I think I should stop there. And next week, I think we're going to look at the local analytic functions of ZP. Also, yeah, Akash, I think the question you were asking, right? So the point is that OF, as topologically, there is nothing that separates it from ZP to the power D, right?
Mm-hmm.
Topologically, they're the same. Just like topologically, like if you look at this, like you can see that the complex numbers is nothing but R plus R. If you're looking at R topology of that, right?
Yeah. Okay.
So then if you're looking at a continuous character from here to here, because topologically they're same, they're looking at the continuous character from ZPD to E star, right?
Okay.
So, and then, I mean, what is, I mean, so like, let's just look at ZP plus ZP, and I mean, of course, this is entirely analogous. So if you have chi, a continuous character is basically what? Like it's chi1 times chi2, right?
Okay.
So chi1 is from ZP to E star, chi2 is from ZP to E star, right?
Okay.
So if you're looking at continuous characters of OF, they are just product of continuous characters of ZP.
Okay.
But if analytically they are not the same, right? Because you can have a function. So you can have a function like, let's say, C alpha X alpha. If C alpha is in Z, only in ZP, it converge. Well, what do you mean by that? Functions with coefficients only in ZP can converge, but not necessarily with OF, right?
Oh, okay. OF is a stronger condition.
Yeah.
Okay.
So, I mean, the corresponding analog is that you can have smooth real functions which are not complex analytic.
Okay.
Right? Like you can have C infinity functions which are not complex analytic.
Okay.
Complex analyticity, for example, like you have this extra condition, I forget what that's called, Cauchy-Riemann or something, right? Like you need like those extra conditions for it to be complex analytic.
So ZP analytic means the C alphas are in QP, ZP, and F analytic means
No, so sorry, it's I should have said the other way around. So okay, now I understand. So this converges. This might converge when X is in ZP to the D. Like if you're interpreting X as like as a sequence of ZP to the D,
okay.
right? And then this might converge on ZP to the D inside OF, kind of. What do I mean by that? So it might converge on the ZP valued points of OF,
Okay.
right? But it might not converge as an F valued function or as a function on F.
Okay. Okay.
That's probably just nonsense. Did I just say nonsense? Probably I said nonsense. Well, I mean, so what I mean is that, like, if you remember, if you want to show that a function from Rn to R, say, right? Like, let's say F, to show if smooth, you can show that components are smooth.
Okay.
Right? Because like, you can think of this as like n functions, each from one component, and it's equivalent to showing that components are smooth or continuous, something like that.
Okay.
But like if you treat now like if it was from R2 to R, you have R, then you can treat it as a function from C to R. But then showing that this is a C analytic means that it's not only showing the components are smooth, they follow certain conditions.
Okay.
So
Okay.
similar thing will creep up here. So to show that because like this has an F manifold structure, right? I see. The point is that like OF is a periodic manifold, but like as what? As ZP manifold, this is just ZP to the D, right?
Okay.
But then you can have like, well, like you can have this as an F analytic manifold, right?
Okay.
So then if you're demanding this character to be F analytic, you're demanding that extra structure of like F analyticity be preserved.
Okay.
And that gives it like extra condition. So basically, I think the condition becomes that this map, like you can treat this, the derivative of the map as a map from ZPD to E, and then this D chi should be F linear. A priori, it is only ZP linear
Okay.
because we are like it's a continuous character of ZP, which continuous character is a locally analytic. So D chi, the derivative map is a ZP linear, right? But if you want it to be F analytic, you want the D chi to be F linear.
Okay.
So I think that's the distinction, and maybe this is a terrible interpretation, but yeah. So yeah, I mean, I think that's like the distinction.
Okay.
Any other questions? Okay. Should we do like CLSZP next time, and then I think that will kickstart the Schneider Teitelbaum paper. This is section 4 of Schneider Teitelbaum's first paper. I mean, we can all read section 4, and I mean, I can talk, but then hopefully it will be more interesting. Did any of this like did some of this make sense? Like at least I mean, make sense in the sense like the big picture sense, because it does not make sense to me very well.
Yeah, a little bit. Yeah.
Yeah, I mean, I'm finding this act of like reading abstracts really exhilarating. I strongly recommend go and read all the abstracts you can, because I have nothing to do because our project is not going anywhere. Uh, okay, so shall we meet next time? Thanks for being here.
Thank you.
Yeah, if you have comments, questions, please just like send any of us, or we can just email each other.
Yeah, for sure.